In this video, we are going to talk about one sample t-test, and I posted the lab inferential stats zipped folder on Blackboard, and basically download that file and unzip it. And then after you unzip the folder, go to the unzipped folder, and then when you open the folder, you will see a similar structure depending on how your view is structured. And I specifically created this one to give you a better view. So to open, first of all, let's open RStudio. And I'll open that one. And from the RStudio, go to the top right corner and click Open Project. And within that project, let's copy this folder path, and then paste that here, and go there. And from here, you will see lab-inferential stats. That's the R project folder, and we want to open that project. So when you click that one, that project will open. So all the files and data files on your computer is basically set to work with R and RStudio that are within this folder. So these files that ends with .r, those are the syntax files, and this data folder includes all the data that we're going to work over time in the lab inferential stats folder. Okay. So, and again, today we're going to talk about one sample t-test, and in the one sample t-test, basically the idea is you want to compare a population mean or a target value with a sample data that you collected. So what do I mean by that? So let's say you are testing a new instructional materials and you recruited 200 freshmen from UMass Boston, and so you teach that group of students with a new teaching material or newly developed theory, and you basically, after you finish your instructions at the end of the year, you collect their GPAs, and you have a GPA for those 200 students. But you can also go to the administration and ask for all the freshmen at UMass Boston for that year, what's their GPA. So basically you have 200 students that you randomly selected from all UMass freshmen, but administration also has that information for every freshman at the school. So basically you want to compare whether the sample that you have, 200 students, their mean GPA is different than overall UMass Boston freshman GPA, because you taught the classes or courses with this particular teaching method, and you want to test whether that teaching method is effective or not. So in this kind of designs, you can use a one sample t-test. Okay. Okay, so the first thing we do is we load the libraries or functions or packages we want to use. And again, DEC tools is the package that helps with the descriptive statistics, and Haven helps with reading an SPSS data file into R. So I'm going to load those two packages and then click Run. And so basically there's no issues, and I'm going to look at the environment. So environment is empty, so I didn't put any data in it yet. And line 11 helps us to read in the data set, but let's do a step-by-step here. So my data is how I am naming the data set that I'm going to read in. So anything, this little sign here, less than and hyphen, is called an assignment operator. So anything on the left is basically, I'm assigning anything on the right to the left with the assignment operator. So what I'm doing here is read SAV comes from Haven. So SAV is an extension for SPSS data file. So read underscore SAV, basically what I'm saying. Read an SPSS file. The next question, like, where is the SPSS file? And then we need to tell the path where the file is. And this forward slash here is saying that I have a data file called one-janet.sav, which is located under a folder called data. So let's see. Let's go to files and check whether that file, data file is there. And click data, and booyah, it's here. The top one is one-janet.sav. So we double check whether the file is in a place that we are, X data file is in a place where we expect it to be. Okay, so you can bring your cursor again at the beginning or at the end of that line and then click run. And basically now we read in the data set. And in this data set, we have 30 observations and 1 variable. So let's open the data set. To open the data set, you can actually click on the name of the file. And if you click this blue, you'll just get more details about the file, but it's not going to open the file. So I'm going to click back that one and close it. But to open it, I want to click the name of the file. So after I do that, it opens the data file. And again, in this file, we have only one variable and 30 participants. And the variable name is KUDI. Okay, we got that information. I'm going to close it. But what happens, or what do you need to do if you don't want to click this? And you basically type view. That's a function that helps you view a data set. And you need to type your data set name in and click run, and it will open it. So, same there. So, one of the things is there are many different ways to do the same thing in R, and this might be sometimes confusing, but that's basically because it's an open source and everybody is working and like in different times and different ideas. So yeah, basically we have many different ways of doing the same thing. And so if you don't want to open the file but want to check your variable names, because we need to call some of those variable names later, and you basically use the names function, you type names, open parentheses, put your data file in and close the parentheses, and let's run that one. So this will print the column names or variable names in your data file. And since we only have one variable, it prints only about variable name. It's KUDI. Okay, so we learned in the descriptive statistics that we can use DEC function to get descriptives on a single variable or with multiple variables, or like for a data set. So to get the descriptive statistics for a data set, we basically type DEC, open parentheses, type the name of your data file and close parentheses, and bring your cursor at the end of that line and click run. So this will give you the descriptive statistics. It will also give you some visuals, but let's focus on that one. So what does this tell us? In this data file, I have 30 observations and log variables. And I have 30 complete cases with no missing data. And this is the result. So I have my N is 30. Like I have no missing data. Unique basically tells you how many unique cases you have in your data. So 22 is basically some of the values are repeating. I have no zeros in this data set, and the mean is 54.63, and median is 55, and the range is 51, and the standard deviation is 10.33. So this gives us some idea about how the data looks like. Okay, so the next several lines, line 22 to 26, this kind of gives us a background information. Basically, KUDI means that Kansas University Depression Inventory, and it looks like this measure was standardized to have a mean of 50 for male adolescents. And again, there's more story. So, and if I want to test a hypothesis that whether the data Janet collected, the 30 cases, the mean for that 30 is significantly different than 50 or not. So the first hypothesis is, and it's saying that it's a two-sided hypothesis. Basically, I'm saying that the mean is different than 50. I'm not saying it's less than or greater than, I'm just saying it's different than 50. And then this is the alternative hypothesis, and the null hypothesis is always the mean is basically 50. There's no difference between the data that I collected with the population mean. Okay. And before I run line 30, I'm going to clear up the console. And to do that, you need to click this top right. There's kind of a grayed out blue. If you click that one, it will clean up the console. So let's run line 30. But before we run, let me explain the syntax. T-test is the function that we want to use. And the first argument is, what's the variable that your data is included. So in this case, I have only one variable in this data set, but I still need to call the variable with its name. And to do that, what you need to do is you type your data set name, my data, you add the $sign after that, and you add the variable name at the end. And mu is what you are testing against. So in the population, it's believed that the mean for KUDI is 50. And basically, I'm testing whether the data that I collected is significantly different than this mean of 50. And my hypothesis, alternative hypothesis, I'm just saying different. It might be less or greater than 50. So that's why I'm calling two-sided. But if I want to have a directional hypothesis, I can type greater. So the mean in my data set is going to be greater than 50. And the other one is the mean in my data set is going to be less than 50. So this is basically how we specify that. So by changing alternative, you're changing your hypothesis type. Okay. So that's on the first one, line 30. Okay, if we run that one, R is going to tell you what type of test that you are. R is telling what type of t-test that you are using, and it's called one sample t-test. And again, we already knew that because that's what we want to do. And R is telling you the variable and the dataset name that you are using. The t-test statistic is 2.45, and the degrees of freedom is 29, and the p-value is 0.02. So the p-value is basically less than the accepted common threshold of 0.05 in social sciences. And so less than 0.05 means that you reject the null hypothesis. So, and the null hypothesis is always, there is no difference. So in this case, we believe that the population mean is going to be 50. And what I'm saying is my data set, my sample, and the population mean is going to be the same. So that's the null hypothesis. But since the p-value is less than 0.02 or 0.05, we are saying that we reject the null hypothesis. So the mean in my sample is different than the population mean. Okay, and that's a significantly different. So the mean in my data set is 54.63, and it's greater than 50. So yeah, we conclude that we reject null hypothesis, and we say that there's a significant difference in my sample compared to the population mean. Okay, so the next one is the direction hypothesis. In this one, we are saying that my hypothesis is there is no difference again, and the alternative hypothesis is the mean in my sample is going to be greater than the population. Okay, let's run that one. Okay, so all of the statistics are the same except the confidence interval and the p-value. And the p-value like 0.01, and again, this is less than 0.05. We're saying that we reject the null. And again, null is the mean is 50 in my sample, as like similar to the mean in the population. So there's no difference between my sample and the population mean. Okay, but we reject that null hypothesis, saying that the mean in our sample is greater than the population mean. And that difference is statistically significant. Okay, and the last one is we are saying that the mean in our sample is going to be less than 50. But since we already run the first two tests, we know that the mean in our sample is going to be greater than 50. So in this data set, we are going to fail to reject the null hypothesis because we expect the p-value is going to be greater than 0.05. I mean, I haven't run that analysis yet, but since we run the first two, we know the mean because the mean is not going to change based on the test. The significance level is going to change based on the test type of the hypothesis we have. Okay, let's run line 37. Okay, so again, we run a one sample t-test. This is our data set, the t-statistics, degrees of freedom, they're all the same in all of these three tests, but the p-value. Because in this hypothesis, but we are saying that the mean in our sample is going to be less than 50. But we know that the mean is going to be 54, so it's not less than 50. So that's why we see this large of a p-value. So we fail to reject the null hypothesis in the last example. Okay, that's all for one sample t-test.